Okay, we talked about stability, the definition of stability, how to determine whether or not a system is stable. Now we want to talk about Routh-Hurwitz criterion. Routh-Hurwitz criterion is a method to determine if a system is stable. It's actually a mathematics method. It doesn't have as much to do with controls, but we use it in controls. Okay, so the focus of Routh-Hurwitz is the characteristic equation. So previously, what we saw is that if we determine the location of the poles, it can tell me about stability of the system. But, well, in all the examples we saw, I wrote transfer functions in a factorized manner. I wrote the transfer function as s minus 1 times s plus 1 times s plus 2. So I was giving you the poles. What if I don't give you the poles? What if you have a characteristic equation that is like s to the 5 negative 3s to the 3 plus 12s squared negative 17.5? How would you solve that? How would you determine if without using your calculator, how would you determine how many of your poles are on the left hand side and how many of them are on the right hand side? That's what Routh-Hurwitz is trying to do. So this is how Routh-Hurwitz works. This is the definition. You have a polynomial. You first need to populate this table, which is called Routh-Hurwitz table. The first two rows directly come from the polynomial. So you put the coefficients in this table. The first row is s to the n. So you put in this row an minus 2, an minus 4, an minus 6, 2a0. In the second row, you put all the coefficients of odd terms. So you put an minus 1, an minus 3, an minus 5, blah, blah. Okay. So the first two rows directly come from the polynomial. Then you create other rows from these two. So the third row is created from the first two rows of the table. The fourth row is created from the two rows that are before the fourth row. So the fourth row is created from row number 3 and row number 4. The fifth row is created from row number 4 and row number 3. Using this formula. So what's bn minus 1? Bn minus 1 is this element. To find bn minus 1, I need to multiply an minus 1 with an minus 2, then subtract from it an times an minus 3, and then I divide it by an minus 1. But wait a second, I'm saying multiply an minus 1 with an minus 2, then subtract from it an times an minus 3. That looks familiar. Where have I seen that? This, and then you subtract from it this. I've seen it somewhere. Where is that? Well, if it was this, subtract from it this. So an times an minus 3, subtract from it an minus 2 times an minus 1. Then it would be the determinant of the matrix, which would include an minus 2, an minus 1, n minus 3. So this numerator can be written as negative 1 times the determinant of matrix an minus 2, n minus 1, n minus 3. So that's one way of writing it. Okay, so that was bn minus 1. How would I find, so again, bn minus 1 is this, subtract from it this, and then divide by an minus 1. How would I find bn minus 3? Well, it's again this first column, but rather than doing this, now you do this. So an minus 1 times an minus 4, and then you subtract from it an minus 5 times an. So you keep this first column, but rather than using the second column, now you jump to third. So now the relationship is in between these two columns, and that is how you find bn minus 3. I'm talking about this formula. Now, how about next row? How would I find cn minus 1? Well, I just shift. So now to find cn minus 1, I do this. To find cn minus 3, I use these two, and then I use these two. So I do bn minus 1 times an minus 5, subtract from it bn minus 5 times an minus 1, and then divide it by bn minus 1. Okay, so that's about the table. I haven't told you the Routh-Hurwitz rule yet. I have an equation or a polynomial. It's the characteristic polynomial of my system. I populate the first two rows directly from the equation, and then I build or populate the other rows of the table. So what? I'm going to end up having a table. So I'm talking about stability. I'm not talking about a table. How would that table help me with stability? Well, look at the Routh-Hurwitz rule. Routh-Hurwitz criterion states that the number of roots of the characteristic equation with positive real parts. So the number of roots of the characteristic equation with positive real parts, meaning that they are on the right-hand side or unstable. They are equal to the number of sign changes of the first column. So I have this table. If I look at the first column, forget about the rest of this table. Only the first column. So if I look at the first column, the number of sign changes between these elements or numbers tells me how many poles are on the right hand side, and basically how whether or not the system is unstable. So let's skip this example. Let's work on a numerical example. I have this polynomial and I want to apply Routh-Hurwitz criterion to it. Well, first I start populating my system. So I write S4, S to the 3, S squared, S to the 1, and S to the 0 on the left-hand side of the table here, or as the index of the table. Then I put 1, 1, and 3 as the first row of the table, and then 4 and 2 and 0 in the next row. Then I want to populate this row. How would I do that? 4 times 1, subtract from it 2 times 1, that would be 2. Divide by 4. 2 divided by 4 is half. To find this element, I do 4 times 3, subtract from it nothing, so 0 times 1. 4 times 3, subtract from it nothing, divide by 4, it's just going to give me 3. So I found the third row from the first two rows. Now I want to find the fourth row. I want to find this element. How would I find this element? 0.5 times 2, that would be 1. Subtract from it 3 times 4, which is 12. So 1, subtract from it 12, it's negative 11. divide by half. Negative 11 divided by half is equal to negative 11 times 2, or negative 22. This element would be found by multiplying 0.5 by 0, which is 0, then subtract from it nothing, times 4, which is again nothing. So it's going to be 0 minus nothing, it's just 0. And then you can find out the last element here. So I populate this table, then I look at the first column of it. How many sign changes do I have? This is a positive number, this is a positive number, this is a positive number, this is a negative number, this is a positive number. So I have 1, 2 sign changes, and that means that I'm going to have 2 poles that are on the right hand side of the j omega axis, and I have instability. If I use MATLAB and I actually find those poles, I have negative 3.8, negative 0.86, and then these are the 2 poles on the right hand side, so I have instability. How about this? Routh-Hurwitz method. Use Routh-Hurwitz method for this system. Again, first 2 rows, I'm going to have 1, 3, 5 for the first row. I'm going to have 2, 4, and then 0 for the second row. To find this element, I do 2 times 3 minus 4 times 1 divided by 2. To find this element, I do 2 times 5, subtract from it 1 times 0, divide by 2. And then the next row, and then the next row. And I see again 2 sign changes, therefore my system is unstable. Okay, now I have a feedback system and I'm being asked to determine the range of k. So I have an unknown, I want to find the range of it to have a stable closed loop system. What would I do? Well, I find the closed loop system first, g divided by 1 plus gh. I'm going to have this transfer function. Then I look at the denominator, that's my characteristic equation. Now I want to fill out this table for the characteristic equation, so I'm going to have 1 and then k plus 58 in the first row, and I'm going to have 1 and 0 in the second row. I can make the third row, or I can deduce that from the first 2 rows. So this is going to be Routh-Hurwitz table. How many sign changes do I have? Well, this is a positive number, this is a positive number, this, I don't know, depends on the k, the value of k. So the question says, find the range of k for which the system is stable. If I want to have stability, I should have no sign changes in the first column. This is positive, so I must have 58 plus k being positive to have stability. So k should be greater than negative 58. Okay, so this was Routh-Hurwitz table. Now, in the next video, we are going to see special cases of Routh-Hurwitz. They're very important. We are going to discuss both of them, and they give us a lot of insight about the system.